Most people work, live, and enjoy their leisure activities in densely populated environments in an ever more connected and globalized society, which allowed an outbreak of the novel coronavirus SARS-CoV-2 to fully develop into a pandemic due to its prolonged latency period and transmission via respiratory droplets. Having said that, rapid ultraviolet germicidal irradiation and controlled humidification of the air in closed spaces has the potential to revolutionize and refacilitate safer human interaction and the subsequent safeguarding of a prosperous economy. UVC germicidal radiation, or UVCGI, at 253.7 nanometers has been demonstrated to effectively neutralize volatile organic compounds and kill a vast majority of pathogens by disrupting their genetic material with a 99.9% success rate, leaving them unable to propagate, colonize, and harm humans. Though mercury-based UV lamps are the current standard for such lamps, concern regarding the toxic and hazardous nature of mercury led to legislation prohibiting the installation of mercury-based machinery in most public places such as schools. We've therefore decided to use UVC LEDs as they provide high output at peak germicidal irradiation wavelengths with stable performance across a wide range of pathogens. UVC LEDs have superior thermal properties, allowing high current operation for low-cost implementation, while also emitting more than adequate UVC radiation from localized points, covering a larger area and enabling predictable performance due to consistent emission patterns. One consequence to using UVCGI is it lowers the humidity of the air. This is problematic because variations in air humidity levels have been proven to drastically alter the infectivity of a virus. A 2019 study showed that the H1N1 novel influenza A virus retained on average 74% infectivity at a relative humidity, or RH levels, below 23% and 18.4% infectivity at RH levels above 43%. Respiratory droplets at low RH levels tend to evaporate faster, while shrinking in size and increasing the possibility of inhalation of droplets with diameters smaller than 10 micrometers. Additionally, dry air can lead to epithelial damage, desiccate nasal mucosa, and reduce mucociliary clearance, increasing susceptibility to SARS-CoV-2 and other respiratory infections due to an inability to entrap and remove pathogens from the airway. Impure air from the room is pulled into the UVAIRA device via two air intakes located on one side using one small yet powerful 120 mm diameter 24-watt brushless DC electric motor fan for each intake point, while pure air from the HVAC system takes advantage of the existing pressure in the duct to enter via an intake port in the back bottom right corner. The specific fan allows for 190 CFM maximum airflow and thus approximate maximum air velocity of 7.84 meters per second. Studies have shown that the optimum airstream velocity lies within the 2.5 to 3.5 meters per second range. The air passing through the first chamber is immediately irradiated using two sets of 14 UVC LEDs based on a nitride-type semiconductor chip placed on the top and bottom of the chamber for full coverage. Given that UVC radiation is known to be harmful to humans, negatively affecting the eye's lens and retinal photoreceptor cells, both LED lamps are safely hidden and the fans are covered, preventing eye contact. The pressure generated by the two air intake fans forces the air to pass through a titanium dioxide filter into the humidifier. This filter allows for the photocatalytic oxidation of the contaminants, which, unlike regular air filters that trap and manually remove said contaminants, this chemically alters them into harmless substances. Dry air is then combined with the moisture produced by UVAIRA's heated humidifier. Finally, the fully purified product with 45 to 50% humidity is rapidly released from the 6 vents located on the top and bottom of each of the 3 rectangular openings with controllable width settings using adjustable flaps. UVAIRA's software uses innovative computer technology to take into consideration environmental conditions. It continuously adjusts all numerical components of the air purifier to find the optimal configuration of parameters such as energy consumption, air velocity, fans' angular velocity, volume, pressure, and temperature. Hospitals, schools, businesses, and other large buildings have high volumes of personal interaction and need to reduce air contaminants. In addition, airplanes, boats, trains, and buses can greatly benefit from the installation of UVAIRA units to reduce infectivity of pathogens. UVAIRA has been designed with an easy-to-follow user interface that allows for use in households and is made of readily available materials. Cost was also an important consideration, so it can be affordable for consumers and promote quick integration of these devices into society. Amidst a pandemic, individuals and institutions bear the burden of financial troubles, and UVAIRA aims to allow life to return back to normal when combined with UVC surface cleaning technologies and other cleaning solutions. Our design is a scalable model that can be easily changed to accommodate indoor areas of various sizes, so any space can benefit, and it fits the needs of the market and can adapt to the progression of coronavirus pandemics. Ultimately, a device like UVAIRA aims at creating a safer environment without relying on societies to drastically change their social norms or existing infrastructure.